Hi everyone. We are Group 7 and our topic is altruistic scheduling in multi-resource clusters. This paper was written by Robert Grandel, Mosharif Chowdhury, Aditya Akela, and Ganesh. The introduction, exploring new horizons in computing. Today, we're delving into the research paper that addresses challenges associated with resource allocations in computer systems. Our focus is on the carbine concept, designed to enhance the efficiency of modern cluster schedulers. Traditional schedulers often prioritize instantaneous fairness, affecting performance isolation between users and groups. Carbine, however, proposes an altruistic long term strategy. It allows jobs in the cluster to voluntarily yield fractions of their allocated resources, optimizing overall efficiency without compromising their completion times. This innovative approach marks a significant shift from conventional methods, paving the way for more effective resource management in computing environments. The problem, the resource allocation challenge. In this segment, we address a critical issue in large-scale computing systems, the challenge of assigning and managing resources of numerous tasks. The key is to achieve a delicate balance where the system is fair to each task, which ensures efficient task completion and maintains overall system performance. This is particularly relevant in environments where multiple tasks compete for limited resources. The paper highlights that short-term convergence to fairness often does not translate into long-term benefits, underlining the need for a more dynamic and adaptive approach to resource allocation. The next is the importance of the issue, why efficient resource allocation matters. This matters because understanding and resolving the problem of resource allocation is vital. Efficient resource allocation is crucial to the performance of large computing systems. It significantly influences how these systems handle complex, simultaneous tasks. Effective management of resources is essential for the system's optimal functioning, directly impacting their ability to perform tasks both quickly and accurately. This segment underscores the importance of efficient resource allocation in enhancing the functionality and responsiveness of large-scale computing environments. This talks about the author's perspective, the drive behind this research. The authors of this paper present a strong case for the need to address the resource allocation issue. They highlight the shortcomings of current scheduling methods, which often prioritize immediate fairness but overlook long term efficiency and overall system performance. This perspective suggests a need for a more holistic approach to resource management, one that balances immediate needs with long term system health and efficiency. This is the author's continuation of the author's perspective, the drive behind the research. In this figure, two schedules are compared, assuming simultaneous arrival of both jobs. The comparison illustrates how traditional scheduling methods might fail to optimize resource allocation when faced with simultaneous competing demands. This highlights the necessity for a scheduling method that can dynamically adapt to changing requirements while maintaining fairness and efficiency. Beyond theory, the implications. Practical implications. The practical implications of Carbine are significant. Theoretically, it contributes new ideas to the field of computing, specifically in the area of resource scheduling. And practically, these ideas have the potential to significantly improve the operational efficiency of large scale computing systems. This segment explores how the theoretical aspects of Carbine translate into tangible improvements in real world computing environments. Continuation of Beyond Theory, efficiency in various work. Carbine consistently improves efficiency across different benchmarks such as TPC-DS, TPC-H, and Big Bench, and production traces from major companies like Facebook and Microsoft. It offers up to 2.85 times improvements in large-scale environments, maintaining fairness. Carbine closely matches the fairness of DRF and even improves in certain scenarios, ensuring equitable resource distribution, especially in dynamic workloads. Optimized resource utilization. By effectively allocating leftover resources, Carbine enhances the overall utilization of the cluster, demonstrating substantial gains in job completion times, particularly for shorter jobs. Minimal scheduling overheads. Carbine introduces only a negligible increase in decision-making time and memory usage, efficiently managing complex matching logic and ensuring smooth integration into existing systems. Existing solutions. Current solution in resource scheduling. This slide presents the existing methods in place for resource scheduling, such as dominant resource fairness, DRF, shortest job first, SJF, and Tetris. Each method focuses on specific aspects like fairness or efficiency, but has limitations in providing a comprehensive solution to resource scheduling. The existing methods specialize in certain areas but fail to address all key aspects of resource scheduling, often overlooking the long-term effectiveness and overall health of the computing system. These are some of the existing solutions. This slide delves into the details of existing solutions in resource scheduling. Dominant Resource Fairness, DRF, is a scheduling algorithm used in Yarn for inter-job scheduling, ensuring fairness in resource allocation among different jobs by considering their dominant resource demands. It's also well suited for balancing resource distribution and multi-resource environments. Next is the shortest job first, SJF, which is a scheduling strategy that prioritizes jobs based on their expected duration. It aims to minimize overall job completion time by scheduling shorter jobs first, but may not always consider the fair distribution of resources or the system's long-term performance. The last is the Tetris, which is a scheduling method that focuses on optimizing the cluster's resource utilization. Its fairness parameter can be adjusted, but its primary focus remains on maximizing efficiency.
Current solutions in resource scheduling. This slide has a graph that compares the performance of three resource scheduling solutions: Tetris, Dominant Resource Fairness, that's DRF, and Shortest Job First, SJF, across three metrics. In interjob fairness, measured by Jan's Fairness Index, DRF leads, indicating a more equitable distribution of resources. For average job completion time, that's JCT, SJF has the shortest duration, suggesting it is the most efficient at completing individual jobs quickly. However, in cluster efficiency, represented by makespan, which is the total time to complete a set of jobs, Tetris performs best, indicating that it uses the entire cluster's resources most effectively over time. Each method has strengths, but none excels in all areas, highlighting the need for a more balanced approach like Carbine. Introducing Carbine, a new solution. Carbine is this paper's innovative solution, where tasks can voluntarily give up resources they don't need, allowing for a more efficient use of the overall system's resources. This concept of altruistic scheduling is a new addition to the evolving field of resource management in computing. Balance utilization is a factor. So carbine reallocates unused resources for overall system efficiency, ensuring balanced utilization without compromising task performance. It also includes a flexible strategy. It adapts to real time changes in resource needs, offering a more flexible approach than the traditional scheduling methods. Efficiency and fairness. It enhances both of these traits as the system efficiency is increased and fairness is also increased by allowing altruistic resource sharing among the tasks. Similarities and differences between this work and existing solutions. Carbine is compared to existing scheduling solutions like DRF, SJF, and Tetris. The main similarity lies in their common goal of efficient task scheduling in the computing clusters. However, Carbine differentiates itself with its unique feature of altruistic scheduling, allowing the tasks to donate unused resources for overall system efficiency, a concept which is absent in the other methods. So, unlike DRF and SJF's immediate fairness or efficiency focus, Carbine prioritizes long term system performance. The paper adequately addresses related work, clearly positioning Carbine as an innovative advancement in resource scheduling. It is definitely worth looking at. Now we move on to the mechanics of Carbine. Carbine's altruistic scheduling approach offers a dynamic, collaborative, as well as a forward looking solution to the challenges of multi resource cluster scheduling, presenting unique features that differentiate it from existing methods. The emphasis on voluntary resource contribution, long term performance focus, and adaptability positions Carbine as an innovative and promising advancement in this field. Moving on to the next aspect of the mechanics, altruistic resource redistribution is one factor of the mechanics. So, Carbine utilizes an innovative mechanism where tasks can voluntarily relinquish resources they don't currently need. This redistribution aims to optimize resource use across the entire system, enhancing the overall efficiency. It also incorporates dynamic scheduling for real time changes. This method is designed to dynamically adapt to real time changes in resource needs of various tasks. This flexibility allows for more efficient scheduling compared to static methods. Combination of efficiency and fairness is also incorporated. Carbine not only improves system efficiency but also maintains fairness in resource allocation. This balance is achieved by its unique approach of redistributing resources among tasks based on their current needs and usage. It also has minimal overheads in implementation. The implementation of Carbine introduces minimal overheads in terms of decision logic and memory usage, making it a practical and efficient solution for large scale computing systems. Its unique approach to resource scheduling, termed altruistic scheduling, fundamentally changes how resources are allocated in large scale computing systems. At the core of Carbine's mechanics is the concept of altruistic resource redistribution, which we have talked about earlier. Furthermore, Carbine dynamically adapts to real time changes in resource needs of various tasks. This is very needed in today's flexibility of it. So, Carbine, like essentially, is very practical for large scale implementations. All these factors that have thus been talked about are key factors for the potential for widespread adoption in resource management systems. So, Carbine's role in advancing computing. Carbine, as presented in the paper, altruistic scheduling in multi resource clusters can be considered trailblazing rather than merely incremental. This is due to its introduction of the novel concept of altruistic scheduling in multi resource clusters. Unlike incremental advancements that typically build upon or slightly improve existing methods, Carbine introduces a fundamentally new approach that we have talked about. By allowing these by allowing altruistically to share unused resources, is it addresses a lot of limitations that are currently present in the traditional scheduling methods that are currently being used, and it significantly enhances overall system efficiency as well as its performance. This approach represents a significant departure from the norm in resource allocation strategies, making it a very pioneering development in this field of large scale computing. Furthermore, in discussing Carbine's role in advancing computing, it is important to recognize that it represents a significant leap rather than a mere incremental step, something that needs to be stressed upon. Carbine introduces this novel concept of altruistic scheduling, which is a very fundamental departure from existing methods. It is a very pioneering development, and it's not just about optimizing existing processes, it's about rethinking the entire approach to resource allocation. By allowing for the voluntary contribution of resources, Carbine facilitates a way more efficient and balanced use of the system's capabilities. The introduction of Carbine thus opens various new avenues for future innovations in this field, potentially influencing the design as well as the implementation of future multi resource cluster schedulers. Proving Carbine's worth. To validate the effectiveness of Carbine, the authors employed a very comprehensive approach. It starts with encompassing theoretical analysis, prototype implementation, as well as simulations. This multifaceted approach was crucial in establishing not just the theoretical validity of Carbine but also its practical applicability. The theoretical analysis laid the foundation, detailing the principles of altruistic scheduling and its potential impact on resource allocation in computing clusters. This analysis provided a strong conceptual basis for Carbine, underlining its potential to revolutionize resource scheduling. Following the theoretical groundwork, a prototype implementation was conducted. Here, Carbine was put into practice, showcasing its functionality as well as feasibility in a simulated real world environment. This step was pivotal in demonstrating how Carbine performs under practical conditions, highlighting its viability as a resource scheduling solution. To further validate Carbine, the authors also ran simulations which test the system under various scenarios as well as workloads. These simulations were designed to mimic real real world challenges, providing a robust test of Carbine's adaptability and effectiveness. Through these simulations, Carbine proved its ability to enhance efficiency as well as fairness in resource allocation across a huge variety of computing environments. This comprehensive approach, blending theoretical analysis with practical application and simulations, effectively demonstrated Carbine's capabilities, ensuring that it is a very big contender in the future of this field. It has like proved its viability through various practical solutions as well as simulations. It is definitely the future for large scale computing systems.
So testing Right. Testing carbine in multiple scenarios. Let's talk about testing carbine across multiple scenarios. When we developed carbine, it wasn't just to improve numbers on a chart, it was to make a tangible difference in computing systems. The effectiveness of carbine was demonstrated multiple times across different scenarios and comparisons. This was not a one time or limited demonstration. The variety of tests, including real world deployments and simulations, ensured that the solution was thoroughly vetted and its benefits were consistently observed. Next slide. Meeting the objectives. As the architects of Carbine, our primary objective was to address the limitations of current resource scheduling methods. Today, I can confidently say that we have not only met our objectives but also set a new standard for how resources can be managed in multi resource clusters. The efficiency of altruistic scheduling through Carbine has been demonstrated, providing a solution that brings balance and efficiency to large scale computing systems. By demonstrating the efficiency of altruistic scheduling through Carbine, they provide a tangible solution that addresses the limitations of existing methods, balancing fairness, efficiency, and performance in large scale computing systems. The paper structures and clarity. The paper is well organized and clearly presented. It logically structures the introduction of concepts, the methodology used for testing, and the analysis of results. When we wrote this paper on Carbine, we aimed for clarity and structure. We wanted to ensure that our ideas were communicated effectively so that anyone, from experts to those new to the field, could understand the significance of the work. The clarity in presentation helps in understanding the complex ideas and innovations brought forward in the research. This structured approach makes the paper accessible to readers from different backgrounds. Next slide. And coming to the evaluation, JCT, job completion time. Carbine marginally trials the best performing SJF in JCT, demonstrating only a slightly longer average JCT. Notably, outperforms other methods like DRF and Tetris in JCT efficiency. Coming to the cluster efficiency, Carbine closely matches the efficiency of Tetris, the leading method in this aspect, showcases a significant improvement in cluster efficiency over other existing methods. Fairness. Carbine achieves near optimal fairness, almost matching DRF, the current standard in fairness. It demonstrates a more consistent fairness index across various time intervals. The overall impact on Carbine enhances both efficiency and fairness in resource allocation, particularly effective in environments with dynamic varying workloads, demonstrates robust performance under different cluster loads and resource contention levels. These graphs refers to the evaluation of the interjob fairness, job performance, and cluster efficiency. Next slide. Improvements across simulation. On the evaluation, a visual comparison. As we move forward in our presentation, let's visually compare Carbine's performance with existing solutions. It's important to note that tangible improvements Carbine brings to the table. When we look at the graphs comparing Jane's Fairness Index, we see Carbine closely matches and in some instances surpasses DRF, which is known for its fairness in resource allocation. But beyond fairness, we also see Carbine improving average job completion time and cluster efficiency, which are critical for the overall performance of computing systems. The bar graphs clearly demonstrate these improvements, and it's these visual representations that underscores the practical benefits of Carbine in the real world environment. It's not just about meeting benchmarks, it's about setting new ones. Next slide. Improvement across simulations. In our simulations, Carbine's impact is consistently positive across various scenarios. These simulations are crucial as they mimic real world applications and workloads. With Carbine, we've seen that not only does it handle typical workloads well, but it also excels when the system is under stress, with high resource contention or with dynamic changing workloads. This is a testament to its robustness and adaptability. It's one thing to perform well under ideal conditions, and quite another to maintain that performance when conditions are far from perfect. Carbine does both. Next slide. So, conclusion. Carbine's impact on resource allocation. Advances in efficiency and fairness. Carbine significantly enhances both efficiency and fairness in resource scheduling, striking a balance not achieved by existing methods. In conclusion, Carbine represents a leap forward in the field of resource allocation. It's not just another incremental step, it's a paradigm shift. So, coming to the practical and scalable solution, it demonstrates practical applicability in large scale computing environments, offering up to 2.85 times improvement in efficiency and closely approximating fairness standards. Innovative altruistic approach. It introduces a novel altruistic scheduling method allowing tasks to yield resources without inflating completion times, leading to collective efficiency gains. In the future implications, Carbine's approach open new avenues in resource management, potentially influencing future designs of multi-resource cluster schedulers. This novel approach has demonstrated up to 2.85 times improvement in efficiency, proving its practical applicability in large scale computing environments. Our scale doesn't just end here, it paves the way for future research and innovation in resource management. The implications of carbon are vast, and and its potential is yet to be fully realized. We stand at the brink of a new era in computing, and carbon is leading the way. Next slide. So, the insights and learnings, key takeaways. And from this paper, we learned about the concept of altruistic scheduling in multi resource clusters, a novel approach to improving the efficiency and performance of large scale computing systems. It introduces the idea that tasks can share unused resources, contributing to overall system efficiency. This approach represents a significant shift from traditional resource allocation methods, highlighting the potential for more efficient and effective computing environments. The research demonstrates the importance of considering long term system performance alongside immediate task fairness and efficiency. Thank you.